Hey there viewers, Erico. Got another car repair video, or a potential repair video I guess. I've got a 2002 Toyota RAV4 that was brought into us. It has a 2.0 4-cylinder in it. And the problem is it won't run a drive cycle, so the guy's not able to get it to pass inspection. He's been combating this problem since August, I guess. He's had it multiple shops. He's taken it to the dealer. They've replaced computers, they've replaced catalytic converters, they've replaced a host of parts. And now he has it here. So, needless to say, I've driven the vehicle. I've put it in check mode. Anybody that's worked on Toyotas is familiar with that. And I've driven the vehicle, and indeed it will not run a drive cycle. It sets the O2 heater, and that's it, and it stops. I've gone through and I've checked all the basic inputs that are going to hinder a drive cycle. You know, whether or not the fuel gauge is working, and brake input, you know, the park neutral switch, cooling temperature, you know, everything from the power steering switch to the, you know, the neutral safety. Anything that can stop it from running a drive cycle, I've gone through and looked at, and everything looks good. The problem is it doesn't set any codes. Obviously because it doesn't run a drive cycle, and you know, my first thought was, well, maybe the PCM, but evidently it's already been replaced. Long story short, I did a little bit of looking on it. I think, I haven't found the information exactly, but just through my experience driving Toyotas, as soon as the O2 sensor heater sets, the next one to go is the air-fuel ratio sensors. So I started looking at those, just kind of looking at data and see what was, you know, what's working and what's not working. And I'm having some problem actually with one of the air-fuel ratio sensors. So I'm going to share with you what I see on the scan tool, you know, as far as air-fuel ratio sensor data. We're going to learn a little bit about those and how to test those because they're kind of tricky to do. So I'm going to share with you what I know about them, maybe fix the problem, and you know, I don't know. I'm really out of answers at this point. I've never been in this situation where I can't find something immediately that's going to hinder a drive cycle. So let's look at this air-fuel ratio sensor. We'll make a video about that and see how it turns out. I guess before we get started, I want to mention that Toyota uses what they call a single-cell linear air-fuel ratio sensor, and they look very similar to just a regular standard oxygen sensor. So I don't want you to be confused. Although they appear to be similar and they look similar and they actually have, you know, 4 wires and same style connector, they work entirely different and need to be tested, you know, a bit differently. So I'm probably not going to go super in depth into the, you know, single cell and dual cell air fuel ratio sensors and, you know, draw this out into a, you know, 5-hour long video, but hopefully we can learn a little bit by looking at this. And like I say, I don't even know if this is going to correct the issue, but we're going to have a look, do a little bit of testing, and you know, see what we find out. And one question I always had whenever I worked on something with an AFR sensor was, why? You know, I mean, the zirconium dioxide O2 sensors have seemed to work well for, you know, for a lot of years, but, you know, some manufacturers choose to use AFR sensors, which are, you know, 3 to 4 times the cost of a normal O2 sensor. I guess the little bit of research I did, it's because they're faster and, you know, more accurate. Other than that, I really don't know. I'd be curious your thoughts on that, or if you've learned why AFRs versus O2 sensors. When you get into the what they call the dual cell sensor, or the lean burn type sensors they use in Hondas, they could detect a wider range of, you know, rich to lean, which I guess I can understand. But other than that, that's just my thoughts. One of the handiest tools you can have for testing an air fuel ratio sensor is enhanced data on your factory scan tool. A lot of times, particularly on these single cell sensors on the Toyotas, they get, how do I say, they get reinterpreted on a OBD2 scan tool to appear like an O2 sensor. So they'll give you false data because you'll watch it, and typically you'll see an O2 sensor, a regular zirconium dioxide O2 sensor, switching from 0 to 1 volt, you know, rich to lean, rich to lean, rich to lean. You know, essentially if it's working correctly. If I was to plug in, I haven't done this on this yet, but if I was to plug in an OBD2, you know, generic data stream on this RAV4, you're going to see the front O2 sensor pretty much flatlined at like 0.6 volts or 0.65 volts. You know, if you didn't know any better, you would probably go after that O2 sensor, like, you know, why isn't this working? Or you would make it force it rich to lean, and you wouldn't see much change. And you know, that's because these air-fuel ratio sensors work, you know, entirely different. So just kind of keep that in mind. It's best, you know, if you have a scan tool, you can look at the enhanced data. That's the best way to test these, to be honest with you. Now that we're over here by the vehicle we're working on, I just want to clarify, I'm not a real good teacher, so I'm probably going to miss a whole lot. It's definitely not one of my strong points. I've got a lot trapped up here that I a lot of times can't get out really well. So if you have any questions, put them in the comment box. I'll do my best to answer it. Now, being that I suspect a air-fuel ratio sensor that's really not working quite right, or it's acting a little bit funky, I guess, we're going to go through and do what I would consider like some dynamic testing first. We're going to test what we can at the plug. You know, a regular O2 sensor, you can unplug it, check the voltage reading coming out of it, and, you know, away you go. You don't even need the car. It creates its own voltage. These are a little different. So we're going to go through and test the heater circuit. Even the heater circuit's different. These heater circuits actually work on a duty cycle, so they're on, off, on, off. And I believe that's because like a regular O2 sensor will run around 600 degrees with the heater circuit. These will run around 1200. So I think the PCM uses the duty cycle to regulate that temperature. So we're going to use this multimeter. We're just going to double check the heater circuit on both air-fuel ratio sensors on this vehicle, and you know, see what they look like. So you can see there, that's how I've got my meter hooked up. I just back probed the two black wires, checking it for continuity. And you can see there on our multimeter, it is 0.0 ohms. So that's what we would expect. I went ahead and checked it to the other air-fuel ratio sensor, and that one read exactly the same, so there's no sense in showing you that. All the tests we're going to be doing, just by the way, are going to be on the O2, or the, keep calling it O2 sensor, on the air-fuel ratio sensor that I suspect is failing. The next test that's pretty simple to do while you're under the hood is just go ahead and turn the key on, put your multimeter in the voltage DC setting, and we're going to check the two signal wires coming from the PCM to the connector on the air-fuel ratio sensor. And this will let us know if, you know, if we have a shorted out wire or an open circuited wire. What we're going to be looking for is one of the wires. Now these are going to be the other two that are opposite the heater circuit. So in this case, it's going to be the two, you know, odd colored wires on the O2 sensor. We're going to unplug it, and we're going to go right into the wiring harness itself. We're going to ground our multimeter on the block. We're going to check one of the pins. It should be 3.3 volts, and the other pin should run around 3 volts even. So I've got my meter grounded right here on the valve cover. I'm going to go into one of the, use a back probe, I'm going to go into one of the terminals. You can see on the voltmeter here, it's at 3.3 volts. Go over to the other terminal, and you can see that one is running at almost 3 volts even, and that's what we would expect to see. That's a good reading. So we know a couple things already. First of all, we know our O2 heater is good in the actual air-fuel ratio sensor, so the heater circuit there is good. We know that the wires running to the air-fuel ratio sensor are good, and the PCM is supplying the correct voltage. The next thing we can do is we can use our lab scope here and check the O2 heater output to the air-fuel ratio sensor, because it is quite critical on these that the heater circuit works correctly, because they have to be so hot in order to, you know, respond quickly to send the correct signal back to the PCM. So what I'm going to do is we're going to plug everything back in. We're going to back probe the heater circuit, and then we're going to check. We're going to look at it on the lab scope. We're actually going to look at the switching graph, I guess is the simplest way to put it, from the PCM, where it's actually turning the heater circuit on and off. It's going to be, you know, 12 volts, 0 volts, 12 volts, 0 volts, and you're going to see this nice square digital wave, hopefully. And then we're going to look at what you could look at with a standard multimeter, which is the duty cycle. And my understanding is when these are cold, that the duty cycle should run around 60% thereabouts, and decrease as the engine warms up, you know, as the air-fuel ratio sensor stays hotter on its own. So let's have a look at that. So there's my air-fuel ratio sensor connector. I've back probed the heater circuit, so the two black wires, I've stuck back probes in both of those, and I've got my meter test leads hooked to them, and then I've got them hooked up to the lab scope, obviously. On the lab scope, I've got that on a 0 to 12 volt scale set up at 200 milliseconds. So let's go ahead and fire it up and see what this heater circuit looks like. So you can see we've got a nice square graph there. It's, I guess, what I would expect to see. This being 12 volts, this being 0. Working on a duty cycle, the computer's going to be turning it on and off. So we can see if we can flick back out of here and actually go look at the duty cycle itself. So there's our duty cycle. This line up here is 60, well, this marks 60 and then 70. I don't know if you can see it or not, but we can see our duty cycles running about 65. So according to information put out by Toyota, well, that's where they run when they're cold. So I'm gonna say that that's a good reading. All right, so you can see that's pretty easy to do a couple quick dynamic tests. Checking the O2 heater, checking the duty cycle, checking the voltage from the PCM. All those tests go pretty quick. So that pretty much wraps it up under here. There is one more dynamic test that you could do. You know, it's a little trickier. It involves running some jumper wires from the O2 heater, you know, 2 connectors, and then plugging in our lab scope to check the voltage output of the air-fuel ratio sensor. I'm not gonna do that because we're gonna just look at the tool data, being that we know that the wiring up here is as good as we could expect it to be. So I'm gonna trust the data that we see on our tool and see if that can help diagnose this a little bit further. Gone ahead and hooked up to the car. I've got the data stream brought up here on my Verus. What we're going to be watching is we're going to be watching air-fuel ratio sensors. Now an oxygen sensor likes to stay around 450 millivolts. At least that's why it's constantly switching from the lean to rich threshold to keep that 14.7 to 1 air-fuel ratio, which works, you know, the best in any modern car. The air-fuel ratio sensor reading is going to be unlike what you see on an O2 sensor. This reading is going to stay around 3.3 volts, 3.1 volts, right in that little narrow window. That's just how they work. When they go extremely lean, say we cause a giant vacuum leak, the voltage is going to spike up around 4 volts. And when it goes rich, the voltage is going to drop way off, somewhere in the neighborhood of 2 volts, the high 1 volt range, somewhere in that area. We can look at this data on the scan tool. Like I said, I expect to see relatively steady readings out of a good air-fuel ratio sensor. I can force the system rich and lean with my scan tool. In this case, I'm gonna bypass that part. I'm just gonna make it rich and lean on the engine. I'm gonna start it up. We're gonna let the air-fuel ratio sensors warm up. Once that's happened, I'm gonna create a big vacuum leak. I'm gonna pull the vacuum line like off the purge solenoid, see what the voltage change does, compare the two, look how they read just sitting at an idle, and then we're gonna enrichen it with you know, probably just a little bit of brake parts cleaner and see how they respond. And then I think you'll see what I'm talking about when I suspect that we do have a bad air-fuel ratio sensor. So there's the data we're gonna be looking at. We've got our air-fuel ratio sensor bank 2 sensor 1, AFR bank 1 sensor 1, and then we've got our 2 oxygen sensors that are after the converter, just up there in the engine RPM. So I'm going to go ahead and start it up. So I've gone ahead and I got the engine running. It's only been running for just a couple minutes, letting it warm up. I've got the throttle pinched a little bit there, about 1600, just kind of help it heat up a little better. So you can see this air-fuel ratio sensor here is what I would expect to see, about 3.3 volts, you know, give or take just a smidge. Now I come over here, this bank 2 sensor 1, and this just is not, it's not a good signal. It's not a good steady reading. It's almost like that air-fuel ratio sensor is sticking per se. So what we're going to do is, being that we're looking at this data, this is the absolute best data to have on a air-fuel ratio sensor. We're going to force it lean and then force it rich and see how it responds to one that I suspect is working good, which is this one over here. Now we're going to watch the data. I'm going to go over here and create a big vacuum leak. We're going to see how it responds. I would expect it to go to a higher voltage, 4 volts or so. a big vacuum hose unhooked right off the purge solenoid. We can see on this one here we're about 3.8 volts, 3.84. But this one over here is only going to 3.45. I really don't think that's good. Let me go ahead and hook the vacuum line back up. We'll let our readings here get steady again. And then I'm going to go ahead and force it rich. So yeah, so look at this O2 sensor, or this air-fuel ratio here. It's just really bizarre how this is, how this is acting like that. It really shouldn't be doing that. Okay, they appear to be kind of steady how they were. I'm going to go over there, I'm going to shoot a little bit of brake clean down the throttle body to kind of force it rich. And we should see this voltage drop right off here down around a 2-volt line, I would imagine. Well, just a minute, let me restart it. I gave it a tad too much. Okay, I've got it restarted. I'm gonna attempt again to force it rich. So we can see by forcing it rich, see the scale here, let me go ahead and just pause this. We can see, let's see if I can replay this a little bit. This one got down, let me bounce her back ahead here. See where it got down to. That got down to 2.18 volts, whereas this air-fuel ratio sensor only dropped to 3 volts. And as I continued to spray it, it wasn't a real steady spray, but we can see this one here was just hanging around about 3.11 volts, so it wasn't responding well to a rich condition, or at least like I think it should. Let's go ahead and just start recording this again. And so I think judging by what we see, watching this data, seeing this air-fuel ratio sensor just kind of flopping all over the place like an O2 sensor, I say we yank it out and replace it with a new one and retest our results. So this is the O2 sensor that I suspect, and this is the one that we were testing originally. This thing's hotter than a Banshee right now. I'm going to use an O2 sensor socket, crack that loose, put on a pair of gloves and take it out and swap it out with a brand new one. This thing's crazy hot. But I want to know now, I don't want to wait till the morning. So I'm just kind of twisting the wires a little bit and wiggling it to get it to unscrew. Got it. So I've got this brand new Denso air-fuel ratio sensor. Let's open it up. There's the number on that. Put a little never sneeze on there. See if I can get this in without getting burned. Alright, got that threaded in. See if I can reach down here with this. I'm afraid to touch anything, it's so hot. Oops, I'm going the right way here. All right, I think we got it tight. Let's plug it in, start it up, and check our readings. Well, would you look at that? We've got the new one in. I fired it up. I've got it all warmed up, and look at those readings. The thing holds right nice and steady around 3.3, right where we'd like it. Now I'm going to go over and recreate the same situation. I'm going to create a vacuum leak first, so I'll go do that right now. So I just yanked the line off the purge solenoid. I'm going to go ahead and kick it right down to an idle. That way our effects are a little more exaggerated. But so this is an idle with a massive vacuum leak, and look at these readings we've got. That's great. You know, see that around 4 volts? That's what we would expect. So I'm going to go ahead and plug that in. Go ahead and let our readings get steady back out here. It should respond very quickly. So around 3.3 volts, and sit there and run steady. And now what I'm going to do is go ahead and create a rich condition by spraying in some brake clean. Well, I think the results here, I'm going to go ahead and just pause it. I mean, the engine stalled, obviously. Let's go back and look right in this area where it was when I was spraying it, and just see how these readings compare. So let's see here. So I first started spraying it, 2.53 volts here, 2.6 here. Definitely better than what we had. You can see they're just flatlining there real good. I'm going to go ahead and fire it up again. Let's watch this a little bit more live, and we'll go from there. All right, well, I went and fired it back up there because I did stall it with the brake cleaner because I had it at an idle. But we can see these readings. I mean, if you remember what that looked like before, I mean, this thing was just popping all over the place versus what it looks like now. This is what you would expect to see on a single cell linear Toyota air fuel ratio sensor. Good steady reading, about 3.3. I'm going to go ahead in there and stab the throttle. We're going to watch it go from rich to lean and then right back steady again. I'll jump on the throttle a couple times there while you watch this. So you can see what happens there. You know, we can watch the oxygen sensor or the air fuel ratio sensor jump right up to a lean condition there, giving it a big gulp of air, and then you know, flatten right out on us. So I'd say we fixed it. All right, viewers, I hope you like this video. It's a little bit different than what I normally do. I usually don't get too techie with stuff or dig too much into stuff, just because I like to ramble a lot. I would love to go through and explain in depth on, what I know about air fuel ratio sensors and all the hundreds of different ones, and well, not hundreds, but the 3 or 4 different kinds that are out there and how they work. But I just hope that looking at this live data, seeing that air fuel ratio sensor on something that, this thing wasn't even throwing a code. The only problem this car has is it won't run a drive cycle. They've had it, like I said, they've had it at the Toyota dealer, they've had it at, multiple other shops, they've changed computers, they've changed, numerous parts. Will this make it run a drive cycle? I don't really know. I mean, I'm going to put it in check mode in the morning, and I'm going to take it for a shake and see if it does. I don't understand it, but I do know it would run the O2 heater, and then it would get to the O2 sensor test and just it would never run it. It would just sit there. So O2 wouldn't run, and then the catalyst wouldn't run, and the evap wouldn't run. And it's my suspicion when this one does run, this thing here is pretty rotted. I mean, I did an independent test on the evap system just to kind of check some bidirectional functions of the computer, and it's going to fail for evap codes because it won't even pull a vacuum on a tank. But that's beyond the point. Maybe that'll be another video, but. At any rate, I hope this helps you understand how O2 sensors vary slightly from oxygen sensors in their reading on the scan tool. Like I say, if we were looking at this in the OBD2 generic side, you would have just seen a steady reading of like 0.66 volts. That can be very confusing with Toyotas and how they interpret from your factory scan tool data to a generic data. So I guess one last thing before I conclude with this video is I mentioned earlier that these air fuel ratio sensors and oxygen sensors are sometimes interchangeable, and you'll find them on listings on the internet where you know, where you could buy one, you think you're getting a bargain, because quite frankly, air-fuel ratio sensors are expensive. So I think we may have solved the mystery. This is the one I took out. This thing is like brand new, and this is one that somebody's probably replaced amidst one of the shops that it's gone to. So I found those numbers on there. I hopped on my good friend Google, and this thing comes up as an oxygen sensor for 2002 Toyota Avalon. The connector was 100% correct, but this is nothing more than a mere O2 sensor. So I think we made a proper diagnosis. Is this going to stop it from running a drive cycle? Well, I'm going to find out tomorrow. I hope so, because then I'll achieve hero status. But besides that, I think we made a good fix. It was a good discovery, you know, just watching some scan tool data, seeing something that's broke without, you know, generating a code, and something that may have been self-inflicted. Simply because, you know, customer probably wanted to save a few bucks, or, you know, shop was trying to make, you know, maximum profits on the cheapest part at the most expensive price. I don't know. It's all speculation. This thing's been so many places, I don't even really know. All I know is it works. That's how an air-fuel ratio sensor works. That's what it looks like. So I'm going to stop babbling on, so you have to quit listening to me and go about my day. So I hope you enjoyed this video. Give us a thumbs up if you did. I give you the thumbs up for sticking with it and making it all the way this far. So I guess I'll conclude with this. Like us on Facebook, and just remember that if I can do it, so can you.